work with CDT out of Kansas City. I specialize in Creo simulate products that includes Mechanica, Mechanism, and many others. But as of now, we're going to be talking about mechanism dynamics, and I'm assuming that people know how to create mechanisms, and then I'm going to try and show you some cool features that most people ignore in mechanisms. So Rosalinda, if you can run the little poll and we'll get started.
Okay, here we go. I have a few questions for you. I have 2 more questions.
Yeah, wildfire 2. Dang.
We have 1 more. That'll do it. It's all yours, Sukumar.
Is that Rosalinda?
I sure am. It's all yours now.
Alright guys, so assuming that you guys know how to create these mechanism connections in assembly mode, we will be talking about mechanism dynamics with Creo Parametric 1.0. Now, the Creo ribbon interface is consistent with the Creo 1.0 interface. They have the same icons, kind of ribbon on the top. You have a lot of new enhancements which we will be talking about, like say 3D contact, ball and bearing connection limits, table motors, gimbal joints, and bushing loads, and all those kind of good jazz. So here a little preview of the ribbon user interface. So you can see that it's very consistent with what Creo is all about. It has ribbons, it has tabs, it has icons. You can completely customize all these ribbons to have your own icons so that you don't switch between tabs rather than, you know, you jumping over from one tab to the other tab to find an icon. So all I'm trying to say is it's just consistent throughout. Now, this is one of my favorite enhancements. We're talking about closed cam snapshot constraint. Okay, it's much easier to set up constraints with the lift off. You can see at the bottom right here where my mouse is, you can enable and disable lift off for cam connections in snapshot window. All right, now you actually don't need to set up. There's no timeline, you know, time setting before a solution starts. You can use like termination conditions to stop the analysis if you don't know when or at what time a certain condition is going to arrive. You can also look at some measure enhancements. You can see that the measure results are user selected coordinate system based. So you can say, hey, tell me the force acting on this body. So you can select a body. It's not limited to joint axes. It can be on a body, and it can be with respect to any user selected coordinate system, which makes it much more easier to kind of compare with your experiments that you do, you know, on the field. This is also a great enhancement, one that I've been asking for since Wildfire 3, which is a different type of fit in a table kind of motor. So instead of having a linear fit, which we always had, which goes straight lines like this, you can actually have a spline fit. You can also have a monotonic fit where you have, like, smoother transitions between each point. And if you look at the very bottom, you can see that you can be asked to show the user points or the interpolated points, or show both, for you to kind of like visualize how the motor's profile is going to be. Okay, so these are good enhancements that can help you to simulate the real world situation much more accurately. Again, with respect to 3D contact, see, earlier it used to be cylinder to a cylinder, or that kind of deal. Now you can actually use partial surfaces, say only a segment of a cylinder or a segment of a sphere. Say for example, earlier you want to simulate like a water slide. So you want to have a ball and you want to roll it along the water slide. Now that couldn't happen in a 3D contact. So now you can actually do that in the 3D contact, which kind of tells you, okay, when the ball rolls because of gravity, is it going to fall off or fly off because of excess speed? Do you need to bank your ride a little more? So you can do those kind of things with the 3D contact. Also, another thing is, if you look at the bottom, it says ball and bearing connection limits. So you actually get a cone angle to tell how much a ball joint can move, which really helps in limiting the range of a ball joint. You can also add a coefficient of restitution. You can also see that when you set these limits and when you drag, it will actually follow these limit rules within the drag deal. Another good thing is the conditional termination of analysis. You can say, hey, I create a measure. Let's say a distance between point A and point B is 10. I want you to stop when the distance is 1. Or when the force goes below 500 newtons, stop it. So you can have these conditions to terminate your analysis, which is again very good. Now you also see the new type of a joint called a gimbal joint. Okay, a gimbal joint is exactly like a ball joint. In a ball joint, note that you use point-to-point references, and you cannot really restrict the range of motion or set axis limits and stuff like that. So you can do all this. Looks very similar to the regular Creo parametric that we're going to be talking about. So go through is basically go ahead and pick the rotational axis, enter a K value, enter a U value if you want the spring to be stretched or not stretched. Okay, so what I'm going to try and do here, I'm going to go ahead and suppress both these springs at the very bottom. See, there is a spring over there and there is a spring over here. I'm going to suppress them. All right, and then I'm going to try and run a static analysis. So you can see static analysis, and in the static analysis you can lock certain entities, okay, cams or whatever. You can lock all of them. I've enabled the gravity, and notice I am not using any loads. Now gravity can be applied from here, the very top. You can see units, magnitude, and the direction of gravity. So what I'm going to try and do is I'm going to run this static analysis, and you can see that that's what happens. Now the reason the static analysis stops where it stops is because I have motion axis limits set to where you're not supposed to move past a certain value. Okay, so that's the result of your static analysis. Now I'm going to also try and show you how to do the forces. So here's the force. I'm going to do an edit definition. You can see the force is defined by an expression. Okay, and the expression is conditional. There's something called crust separation. Now what is this crust separation? Is every model going to have crust separation? No. A crust separation is something that we created as a measure. So I'm going to try and show you the crust separation measure first, and then we'll talk about the forces. So if I go to measures, see right here, so I'm going to say, give it a name, whatever custom name we want. We say separation as a type. We select a point at the top, and we select the point at the bottom right here, and we say OK. So it's basically measuring the distance. Okay. So what I tell it here in the force deal is that, sorry, not this one. So I'm telling it right here is this force will act at a value of 600 when the crust separation, which is the distance between that point and this point, is between 32 and 50. The value of the force will be 300 when the distance between this point at the top and this point at the bottom is between 50 and 100. And it's 800 when the value is between 100 and 172. So here I'm using an equation to do that. So add an expression, edit that. See that? So I can say the value is 6,000. So crust separation is 100 to 200 or 200. So I can say equal to or greater than equal to. Okay, so that's how I added these values. All right, so let's get rid of that. You can look at the graph for it. Oops. Hey, what does it show you? Shows me that I'm working hard and I crashed the computer. Give me a second, it's going to come up. Did happen earlier, did now, usually happens in presentations, so I hope you guys used to this crashing deal. Nah, it's not really that bad. It's alright. So there we are. We were talking about crush deal. So you can see the expressions right here. So that's that force. There's a force that acting from the bottom, which is a reaction force of the can. So I'm going to say at time so and so, that's the magnitude. At time so and so, that's the magnitude. And you can see we were talking about different types of fits. Let me auto hide this. So I have show user points, show interpolated points, or show both. You want to see the magnitude or the derivative of it. Now you can also do a linear fit, a spline fit, or a monotonic fit. Right? So you can do either one. All these options right here in the box when you define a force. So once that's done, we can see that there is an initial condition right here. Initial condition is, hey, I want you to always start the analysis at this position. And then I can say, I want to define an initial velocity to a point. I want to define a motion axis velocity to a point. I want to define an angular velocity, tangential slot velocity, or you can once you define all this, you can evaluate all the velocity conditions. So you can do that too. So may also go ahead and see our springs are back there. We'll go ahead and run this analysis. So you can see that's what happens. Now we can go look at the graph of this crust separation measure. So you can see how the initial separation values are on 172. It goes down to almost 30, stays there, and then it goes back up and stays stagnant. All right. Now all this is good. Like, what am I going to get out of it? Right? Now I need to know, hey, what kind of forces act on this particular part. So I want to send this analysis results into Mechanica. So there is a icon which says use in structure. I don't know where it is, so I go structure, place your cursor there, you see, okay, that's where it is, right? So you can click right there and say, I want this body this component, see that? Say maximum, I want to see the worst case scenario, and I can send all these loads, say okay. Now you can actually select that part. You can also go into Creo Simulate, and we can look for mechanism load. See that right there? And we can import all these loads. So you see all those loads are automatically applied to the part. We can add our constraints, material properties, all that good jazz, and run a static analysis or different types of FEA analysis that we might want to run. Okay, because this being a mechanism dynamics class, I'm going to stop myself from doing that. And I'm going to jump in to my next example. This was just to give you a broad level overview as to how you can use a combination of all these. Now I'm going to show you step by step different examples which show you how to create each of these, like say a spring or a motor or a force, and etc. If there are any questions, just type them up for Rosalinda. I'm going to try and save some time at the end of the presentation to go over these questions. So first things I'm going to talk about is mass property. So let's say we have this particular example, and if I do an edit definition, I want you to see it's a cylinder connection. That means it can slide and rotate. All right. Now I'm going to open this part up real quick. I want to go to the model mass properties. Notice there is no material assigned. I'm going to go ahead and pick steel. Okay. I'm assigning steel as a material property to that particular part. And let's get into mechanism. So note that here I have a spring already created, and I'll show you how I created the spring using a different example. So as of now, let's assume that there is a spring right here, and then I'm going to try and run a analysis. So here I have a dynamic analysis. Also notice that I've enabled gravity. There's your gravity. So when I run the analysis, notice that nothing happens. Why does nothing happen? You have to make sure that you go to this external loads and make sure the gravity is checked out. Even though you applied gravity as a load, if you don't have this button checked out, it's not going to use it. So I'm going to go ahead and say run, and you can see how that happens. Okay. Now I'm going to go ahead, open this part up, go to its property, change the material to say something lighter, which is nylon. So we have nylon as the part material. So you go ahead and rerun the same analysis. So you can see how the part doesn't move as much. Now I want you to also notice that there is no damper applied to the spring, so spring is being really active, right? In the next, in the further examples, we'll talk about springs and dampers, and we can see what kind of effect a damper would have on this kind of data. So that's my second example. The third example would be using a force motor, right? So here's a little deal. So I'm going to go ahead and rotate it so that you can see how this works. All right. So a lot of people ask me, hey, I can do servo motor, but I can't do force motor. So here's the force motor example. So right here in the motors, we can right click, do an edit definition. So you want you to see that the motor connection axis is that. I'm using a ramp, which is A plus B times X, where X would be your time. So that's the variable. You can look at the graph and you can see how the motor velocity or your speed is going to increase. we can look at this definition. I'm using a slider connection axis. See this slider connection axis right here, because I want you to slide this way and say the force value in terms of different units right here, and then that is the magnitude of it. And then you can look at it in a graph, just looks straight. So all we are trying to do is right click, new, pick an axis, say 10. You can use different types of profiles that you might want to use. So you can see different profiles are available for you to mess with and change it. And we can create this motor. Now let's look at some of the analysis result. So I'm going to go ahead and run. You can see. Now another thing about this is that you can go here and you can say, you know what, the whole analysis for 11 seconds, I want motor number 1 to start after 2 seconds and then rerun the analysis. So you see motor number 1 is not started. Now motor number 1 starts after 2 seconds. So you can set when you want it to start and when you want it to end, and that would be a force motor. Okay. All right. The next thing we're going to talk about is springs. So I'm going to open a spring example. Alright, so let's get into mechanism. Spring, notice there is one spring right here, which is a linear spring. See that? We use, see that? That shows it's a linear extension. Now also look at the 2 points that we pick as a reference. Hopefully I have points displayed right there. We pick 2 points. Now notice the icon diameter. I can make it smaller if you want me to, just for display purposes. See that? Spring looks much smaller. You can do it at definition. You can go back to 54. Oops. I did that right. That's really small. You want to do 50. There you go. So you can adjust that display. It doesn't like change anything. Now note that the K value, spring stiffness, is 900. The current value is 140. And the U value, that means the unstretched length of the spring, is 142. That means the spring's not compressed or pulled up. So that's one. I want you to also see there's a torsional spring. For a torsional spring, we use the rotation axis. See that? That's the reference that I'm using. I'm telling them that K value is 200, current is 0, U value is 180. That means it's actually twisted to 180 degrees, as that means it's stretched. So when you go ahead and run this analysis, you can see how that rotates as well as goes up and down. Okay, so that's like a torsional spring and a extensional spring example. So let's also look at dampers. Dampers is also something that people don't use as much, and it's pretty cool. It's very easy to use too. So we know we have these two springs in the same example. Now I have a damper. See, I have a damper for the extensional spring and I have a damper for a rotational spring. Not necessarily that I have both, but I just have it as an example. So let's look at this. Notice it's a rotational damper. That's the connection axis, and C value. So note that the equation that it's trying to solve is mx double dot plus cx dot plus kx plus d equal to 0, where m is mass, x double dot is the double derivative of displacement, so it's acceleration. C x dot is a damping coefficient times a single derivative of displacement, which is velocity, and kx is stiffness times x, which is displacement, and d is a constant. So that's where the C is going to be used to do that. So you have rotational damper, and then you also have an extensional damper. You can see we use the translation axis right here, translational axis, as a reference for C. So you can see when you run this analysis, you can see that's where it stops, because the damper takes care of all the other motions. So you can use a combination of spring and damper to actually simulate more realistic situations. Next thing that I'm going to talk to you about is friction. So let's say, how do we use friction to kind of go ahead and, you know, solve some of the problems. In friction, there is also some parameters that I want to cover with you guys. So let's look at friction, and the parameter that I want to cover with is something called restitution. E represents restitution. It is the ratio of velocities of the two bodies before and after the collision. In simple terms, if you have an E value, then that means, you know, if you take a ball and let it bounce and there is no E, then it'll keep bouncing till the end of the world, right? If you have an E value, it will slowly die down. So it eats up the energy. So that's what E value basically represents in simple layman's terms. So here I want you to see that there is a cam connection. So I'm going to edit definition. Notice that you pick a surface right there, cam surface, and then you pick another surface. So those are the two connections, two surfaces that I use for cam. Now this is the most important part. What I'm trying to do is I'm going to disable all these. See, that's E value, which is the coefficient of restitution, and then there is something called liftoff. Okay, when I disable the liftoff, that means the two surfaces will always need to be in contact. Okay, so I'm going to try and run this analysis, and notice there is no rotation. That little cylinder is not rotating; it's just moving or sliding. I go ahead and start the liftoff, and I start off with the coefficient of restitution, and I enable friction. You can see how you're enabling the liftoff, though the connection need not be constant. You can see it's sliding too. So I'm going to just run a playback on this one real quick for you to see. So you can see it rolls, and then right now it's going to slide a little bit. See that? That's slippage, right? So if you don't enable liftoff, that's not going to happen. Now, similarly, we can go ahead, play with the parameters, and say coefficient of restitution is 0.5, friction is 0.5 and 0.3. See, notice that static friction needs to be always greater than the kinematic friction. So let's go ahead and run this. You can see that because the coefficient of restitution has increased, it dies down fast. It doesn't make many circles. Okay, so liftoff will enable the separation between the two cam surfaces, and coefficient of restitution tells you how quickly this motion is going to die, because see, it's all moving because of gravity. And then friction can enables you to slow down the motion. The higher the friction, the faster it dies down. So you can use a combination of both of them to kind of get like a desired result. Alright, that being said, let's talk about applying forces. So I want to apply a force or a torque, right? So how do I do that? I have a simple example. Note that this little part is connected by a planar joint. That means it can rotate, it can translate along this surface, but cannot move away from the surface. All right. So let's get into mechanism. Now in here, I have two forces applied. Where are my forces? There you go. So the first force that I'm applying is a point force. See that point force applied to that little point right there? It's constant, and that's the value of it. And the direction is specified right here. So that's the constant direction in which the force is being applied. Now, next force is body torque. Notice I used point force earlier, now I'm using body torque. Alright? So in a body torque, I'm saying again it's a constant, that's the value, and y direction is specified. That means it's going to rotate about the y axis. Okay? So let's go ahead and look at the analysis. Now notice that it's running for 17 seconds. There's no motors. There's gravity and friction enabled. Notice that the first force, the point force right here, runs from start to the end. The torque starts from 7 seconds to end, where end is about 17 seconds, so it runs for 10 seconds. So you can see. Now, notice how the force, it changed direction. Why did it change direction? We didn't ask it to change the direction. So you can see how it's moving one way, see that way, so it should actually end up here. But notice it's hitting it there and then it goes straight. Now what happens here is that if you look at the assembly connection, you have a translation axis limit which says it goes from -28 to +28, which is this surface. So that means the connection is not letting it go past it. Now it's here. In that direction is where the force is acting, so it's pushed in that way. If you don't have this limit, it'll just go up. Okay? So the reason it's kind of hitting it here and then going straight is because of this limit which is set. It cannot go more than 28 inches from this plane. And that's what makes it kind of go this way. So you see it goes here, it hits it, and it cannot go past it, so it's being pushed over there. Alright? So that's how you would apply a force and torque deal. Now, all this is dynamic analysis, right? Now, there are two other types of analysis that I wanted to talk about. There is a static analysis, and then there is a force balance analysis. Now, a static analysis tells you what is the static equilibrium position of your mechanism. A force balance analysis tells you what kind of force is required to hold the mechanism in place or keep it motionless. So let's look at these two different example types, and after that I have one more which talks about redundancies, which are pretty much ignored most of the time. So let's talk about those three and then we'll jump into questions. So let's look at static analysis. Like I said, I have prepared for a bunch of different things that I wanted to show, as you can see from these folders, but you know, I don't think 1 hour is enough for that. So I have a little link right here, link mechanism. All right. Now note that I'm applying a force of 50,000, right? That's the force. And then I'm trying to run a static analysis. So in a static analysis, notice I have disable connection. So I have those options right here that I was going to talk to you guys about. So let's say I didn't do nothing with it, right? I'm just running a static analysis. So when you run that, you see that's where your analysis stops, because this force is stopping it from going all the way down. Okay. Now if you disable the connection and you run again, now what is this connection? You can see it highlighted right here. So what I'm trying to say is, you know what, this is no longer connected. What happens? So let's say it starts from there, and you can see when the connection is disabled. I'm going to rerun this. So you can see that's disabled, so it comes down. Alright, so that's there. Now let's also go ahead and add our force torque load and rerun the analysis. So you can see, because the force is holding it, see that? The force is holding it up. Now if I don't disable the connection and run it, that's what's going to happen. So you can see different situations where it attains static equilibrium differently. So you can say, hey, you know what, these two are not connected. Let's run that. That's what's going to happen. That's because of the force. All right. Now, if you get rid of the force and run it, that's what's going to happen. Okay. So that static analysis tells you static equilibrium positions. It's very important that we kind of like take care of this issue, because if the part's not in static equilibrium, and let's say, you know, I'm just giving a hypothetical situation. If you transport this part or this big assembly or a machine, it's not in static equilibrium because of the vibrations on the road or the vibrations induced by the truck that's carrying it, that could result in resonance also. So then your whole assembly starts vibrating much more violently than what it's supposed to. So it's kind of important that we run this static analysis to kind of find out what the static equilibrium position of our mechanism is. Now, that's static. Let's go ahead and do force balance. A force balance analysis is an exact opposite of static analysis. It basically tells me how much force do I need to apply to keep this mechanism in position. Okay, so let's go ahead, get into mechanism. You see there is the force acting on this little part, right? It's at 3.45, so something's pushing it down. Notice that there is a spring right here. Okay, so the spring that's pushing this ball, it's connected to this particular nut. Right, this is pushing this ball. Notice the K value of the spring. Notice the current position is 116, but the unstretched length is 152. That means the spring is compressed and it's pushing it that side. Okay. Now, when you want to run an analysis, especially an analysis like a force balance analysis, what you do is you create these load cells. See that? You just choose force balance and then you create this load cell. Now what is this load cell? When you run this analysis, it's going to basically tell you reaction force at the load cell constraint is 121, whatever units you have, say newtons. That means you have to put a force of 121 units wherever that load cell is to stop this mechanism from moving. So let's see how I created this load cell. So I go right here, say load cell, you have to select a point, then you got to select the body, say the load cell direction. See, this is the Y direction, so it's not acting in X. In Y it is 1 and Z it is 0. So you can see that's where the load cell is. So when you run, it's going to tell you how much reaction force is needed in the Y direction. Now, you can also go say new load cell, same point, same body, but I want to know the reaction force in X direction. So X is 0, Y, X is 1, Y is 0, Z is 0. And then I rerun it. And notice the value that I get is nothing, because there is nothing acting in that particular direction. So depending on different load cell in different directions, you can tell the force. So now I can say I need to push this ball inside here by 121 newtons so that this doesn't move. Now, where is this really helpful? Say, for example, you have shock absorbers, right? Now, I'm going to go through a bump and I don't want the shock absorber to move. So I fix the location, I create a load cell at the piston top. All right. So when I go through the bump, I enter a force. It tells me how much it should be the reaction force at the other end of the piston to stop the piston from moving. Now that would be the pressure of oil that you would need on the other side of the piston to take the shock. So that's where a lot of people use this to kind of like figure out what kind of pressures are acting within a hydraulic cylinder kind of system. So that they know what kind of oil pressure they need to withstand a certain force. Or say, I have a little loader that's carrying a bunch of grain. Then I have to hold it at 45-degree angle. Now my piston cylinder is stretched. So if I have to hold it over there for so much weight, what is the amount of liquid pressure or oil pressure that I need to apply to keep it in position? And those kind of things are generally done using the force balance analysis. Okay, so typically you create a load cell so that it tells you at what point you need to apply what kind of a load to stop this mechanism from moving. So the last example that I have for today is redundancies. I want you to see this simple door example. Okay. Now notice that there are two locations. See this? Two locations. Now you would create a pin joint right there. See, pin joint. Okay. Say we use the pin joint to create this. Now that should be good enough because this is the software. Mathematically that's good enough. In real life you might need a hinge or a cylinder at the top too. See what I'm saying? Even at the top. But notice this constraint is disabled. Why am I doing this? What is the point over here? The point is, by using a pin connection, this component is connected to this particular component. Okay? And that will allow this degree of motion like that. Okay? You don't need to again add another constraint which will restrict or enable the same degree of freedom. Again, there are 6 degrees of freedom, 3 translations, 3 rotations. So by adding this hinge cylinder, I am unnecessarily restricting the same degree of freedom and enabling the same degree of freedom. Okay, so as of now I'm going to disable this. So just imagine that I only have a pin connection. Now I get into mechanism. All right, now I run an analysis, that open and close, and now I look at the measures. See that there is degree of freedom and redundancy. So there is 0 degree of freedom because of the force acting and the spring over here. There is no degree of freedom. It's completely shut down, closed. Now what I do is I go here and I take out the force, say, or take out the spring. So let's suppress the spring. So there is no spring. And when I run the analysis, I also get rid of the force. So there's no force, nothing. So I run the analysis and then I look at the measure value. Okay, so look at this. It says it has 1 degree of freedom. Because there's nothing stopping it from moving, it says it has 1 degree of freedom, which is 1 rotation, and there is no redundancies. That means there is no other connection kind of repeating the same thing, right? Making it redundant. Let's go back again. And right now, I'm going to go ahead and enable this. This is the common mistake top and at the bottom. So we go ahead and enable it. All right. So now notice it has 2 connections, which makes it do the same thing. So now I go into mechanism. And I'm going to try and run that analysis again. See that? No motors, no external loads. I just go ahead and run it. Stays where it is. notice that in our measures we can see there is 1 degree of freedom, but there are 4 redundancies. See that? Now, what is this redundancy? Degree of freedom is calculated by, say, 6 times, because there are 6 degrees of freedom, 6 times the number of bodies. Here there is only 1 body, minus number of connections times degrees of freedom per connection. So number of connection is 2, degree of freedom, total degree of freedom, you calculate that and you can see there is 1 degree of freedom that is there available. But here the problem is there are 2 connections doing the same job, which makes redundancies, and that's why you have 4 degrees of freedom which are redundant here. Okay, so this will kind of give you problems in terms of your results at connection joint analysis, joint axis connection results could be wrong. I cannot trust them because my system has redundancies. So you have to make sure that your system doesn't have redundancies. So how would you kind of create these measures? Because these are not created by default. You would say new, you can give it whatever name you want, and you go here and say, you see one is for degree of freedom and the other one is redundancies. Okay, so you can say that, and there you have it, shows you the redundancies. All right, so that's what I had for today, and it is 12:50, so we got about, and also I want to cover all these things without skipping. Like you guys could see, we pretty much have all of these that I wanted to go over, but time constraints, I just picked the most commonly not used capabilities. So Rosalinda, how do I unmute everybody for questions, and do we have any? It says RTS going.
That was from earlier.
Okay. So are there any questions, or do I get to have my lunch?
Okay.
Everyone's unmuted now.
Okay.
I guess there are no questions.
None here. Thank you.
Okay, I guess that'll do it, Sukumar. This recording up on our YouTube page as well.
The organizer has ended the session, and this call will be disconnected. Goodbye.